Okay, this video, I'll probably make it in two parts. It's the first part, otherwise they go on too long. They're very hard getting YouTube otherwise. Anyway, this one is all to do with stationary waves. And hopefully I'm going to explain the following, which is below. You should be able to label nodes and antinodes on a stationary wave. It explains what these both are. Explain how a stationary wave is formed, stating the condition needed for the formation of a stationary wave using a graphical method, and link the distance between nodes to the wavelength for a stationary wave. And then finally, we can compare and contrast stationary waves and progressive waves. So I'm going to miss that out. I'm going to go straight to here. Where I normally do this is, I'm going to get this, hopefully get this software working, is I would use Slinky in front of you, but unfortunately I can't use Slinky, therefore, oh dear, there we go. I'm going to use this instead, which I've now eventually got to work. By using a Slinky, what I'll do is show you how a wave is formed. So imagine this is a string on a bench, okay, and what I can do is I can wiggle this end and off goes the wave, okay, and the wave travels down. Now as I flick this, I'm sending a progressive wave all the way down here, and it comes back again, and it's reflecting off this end here. Remember, the particles vibrate up and down this way. At no time the particles go along the wave, and therefore we should be happy now. This is going to be a transverse wave. Okay. Now, as I mentioned before, reflection happens at that far end. But if you look very carefully, and it's quite hard to see, but I hope you can see it, as the wave goes down, if it's going up here, when it reflects going down. Have a look, so you can see it. You should be able to see it. It's another pulse out. So if that was going up here and reflecting was going down. Therefore, hang on, there's going to be reflection, but isn't there going to be a phase shift? And the phase shift is going to be 180 degrees or pi. Whereas as the wave goes up here, it goes down again. Now, what I can do now is going to make a stationary wave. So if I keep flicking this up and down, it then is going to reflect. But now I've got one wave going left to right, being reflected, and then basically I've got a wave going right to left. But aren't we going to have superposition then? Aren't the waves going to interfere? And I get this going just right now. You can slowly but surely start to see formation of a stationary wave. And the reason why I'm getting a stationary wave is because one wave is going that way, reflecting and coming back the other way again. But when it reflects, you get a 180-degree flip here. And examples of stationary waves, anybody having a musical instrument, waves in a string, for example, also waves in pipes, create these stationary waves. Anyway, how to go doing that there? I seem to open it up 500 million times, but never mind. So to show you to another wave, this is also showing a simulation of a stationary wave. Now here, what you've got is you've got two waves. Now one of them, you've got the wave first of all going top is going left to right, okay? And that's going to be my red wave. And then when it hits the other end, it then is going to reflect back and it's going to go now right to left. Unfortunately, we don't get the 180-degree flip at this end in the simulation. But what I'm going to do now is I'm going to show you really how the stationary wave forms. Because now what I'm going to do is I'm going to put red and blue over the top. And remember, going back to re-emerge them, is the red one is going to the right and the blue one's going to the left. Merge them again. Therefore, we have superposition. Therefore, we have superposition. We can then get the resultant wave, which is going to be in black. Okay, and this, I'll take the merge away again. That is the stationary wave, which you see going up and down. Now, I will quickly stop it. We call these, here is the node. And here, where it goes up and down with big amplitude, is actually called the antinode. So there's a node, here's a node, there's a node, antinode here, antinode there, antinode there, and antinode here. Now, why this forms, well, immersion back together again, it's quite straightforward, really. if I pause it anywhere, okay, here is a node. Well, that goes up by that much, and that goes down by that much. If that was +1 and that was -1, wouldn't it equal 0? Here, they both go down that much. Therefore, if we add those two together, isn't it going to be here? Exactly the same for this one. Here, that is 0, the red one. The blue one's down there. Therefore, the resultant wave is there. Therefore, if I might go forward in time now, you see basically the black wave is all to do with the addition of the blue and the red wave. But always we get hold of a stationary wave here, here, and here. And the stationary wave, a node is always going to be here, here, and here. Therefore, the nodes don't change position whatsoever. And that's why we get a stationary wave. Also, what you've got, and I'll upload the link to it as well here, on Focus e-Learning, you can go and have a look at this, how stationary waves are formed. Because if you go on down to waves, and then go further down here, and go to stationary waves, I don't think it's quite as good as the one I showed before, but you have a play around with it, is now, here's going to be the blue wave now going up to the left, and the red wave left. The blue wave's going to the right, the red wave's going to the left, and here's going to be your stationary wave. And also what you've got is you've got a little video here showing about stationary waves as well. And you can have a look at that at the same time. And you've got examples of stationary wave stream we've got to look at later on, which is also going to be here. But anyway, have a play around with that, and I'll put the link on my little Edmodo post later on. So getting back to here, this is showing you how a stationary wave is formed. Now, an important thing, and examiners love this, is energy transferred. It's a very weird concept. It is not a progressive wave. The wave is not transferring energy along here. Therefore, we say, no, the energy is not transferred going along the wave because no vibration is sent here. That is basically what it means by that, is energy transferred. A regressive wave sends energy from point A to B. This is not sending energy across. But what it does do, admittedly, is make the air particles vibrate around it. Hence, you can hear waves in the string, etc. But it's not transferred along. Now, also what I'll include on the Edmodo post is this document, which is really nice, and it shows you how the wave changes with time. And what you got is one wave going, B going to the right and A going to the left, and they do like you going through the full cycles. In other words, if I take this, the top one, to be 0 time period, and then here, going all the way through here to a half a time period later, a full time period is a wave to go from here to there, to there, to there, to there again. So in other words, if I go through half time period, it's going to be at the bottom. In other words, it was at the top here and then goes to the bottom there. Therefore, if you take your wave going through a quarter of a cycle, it goes from here to there. Therefore, doesn't it make sense if I go to 1/8 cycle, it's going to be here, which is basically going to be halfway from there to there. And you do need to know how it changes with time. If you go to 3/8, it's now gone through the center part, and now it's going to go to down to there, and then a full half cycle later at the bottom there. But you'll find that worksheet attached for you to have a look at. Okay, so have a go at these and answer them. And these are basically what I've been talking about is, and I'm going to stop the video here and I'm going to give you the answer to all these on the next video. And answer them yourself first, and then you'll find the answer in the next video. Over and out.